Okay, so let's start with our lab 4. Okay, so today we are going to build our first machine learning model. Okay, so this is entirely focused on how to create a machine learning model. So we'll not go into deeper in the next lab. Next lab, we'll go much deeper into machine learning model, but today we are going to see the pipeline. Okay, understand the pipeline, how to create a machine learning model. Try to understand it very carefully because there are very small issues. If you don't follow those procedure, your model will actually give you very biased predictions. Okay, there are some issues like data leakage issues and other issues. So you should know the pipeline very clearly. So try to understand and let me know if you have any question. So machine learning model, first of all, you need a data set. Okay, you need a data set and you know how to work with the data. So you have learned pandas. So using pandas, you can import your data set in your workspace. Achha. So these things you have learned in your previous labs. So in the data, you have actually a target column. We can actually divide it into two types. One is your target column. Other is the features. Features or attributes. Okay. Based on these features and attributes, we are going to predict something like this. This is our goal. This is the goal of the machine learning model. Based on the features or attribute values, we are going to we'll try to predict whatever is in the target column. To give a simple example, for instance, one is house rent example, very common. Let's say, we can say, if you have a data set, the data set can have some feature attributes such as the number of rooms. This is one feature variable. Then let's say number of bathrooms. Okay. Then let's say the number of balconies. Okay. Then let's say location. That can be also. So there are different attributes. Let's say based on this, you can actually define the rent. So for instance, if you have a data set like this, so if it is one data instance, it's like number of rooms is one, only one room, one bath, one balcony, and let's say the location is, let's say Uttara 11, sector 11, and the rent is, say for instance 18K, okay, 18,000. Another data set can be and another data instance can be like two rooms, one bath, one balcony. Let's say it is Uttara 10, and the price is like 19K. Okay. You have another instance like three rooms, two baths, two balconies. Location is like sector 4 and it's priced like 25K. Okay. Then another one, room 3, three rooms, three baths, three balconies. Okay. It is in Uttara sector, let's say 13, and the price is like 30K. Like this way, you can have this kind of instances. These are the rows in your data, or what we call them the instance. You call them instance or sample. These are the sample that you have. Okay, based on this sample, we want to predict this one, rent. So your machine learning that is going to learn by itself through some algorithm that if, let's say for a for another one, let's say you have a room like two rooms, two bath, two balcony, and the location is, let's say Dhanmondi. Okay, let's say the location is Dhanmondi. What is the likely rent of this house? Okay, what is the likely rent of this house? This is something you want to predict. That's your task. Okay, so you learn from the data set that you have. You learn from the data that you have and try to predict for some unknown scenario, unseen scenario, unknown or unseen scenario. That's your machine learning task actually. Okay, so through some algorithms, you have different algorithms, you're trying to predict something that you don't know. Okay, so that's what you are going to do. That's the target of machine learning. Is it okay? Any question? Any question? Okay, so as you can see, this kind of data set, you can actually download this. There are different sources. You can actually download this data set. And the example can vary. For instance, like your house rent price, you are trying to predict the price of a house, price of the rent of the house based on certain features. Also, let's say cancer diagnosis, that can be one thing. So different parameters like the size of the tumor, okay, the location of the tumor, size of the tumor, then there are other scenarios. Okay. Other physical attributes, based on those things, you can also predict the diagnosis, whether the cancer cell, it is a malignant cell or benign. This can be one thing. Or also, let's say, for instance, fault diagnosis. Okay. Based on different working condition of your instrument, you can actually try to predict whether there is any fault in the machinery or not. This is one example. Acha. So based on this task, actually, we can actually divide the target and divide the task into two types. One is classification, and another one is regression. The difference is that your target value, this is your target, right? This is your target column. If the target is regression, if the target is numerical value, like the price 20K, 25K, if it is like numerical value like this way, then this is called a regression problem. If the value is like 0 or 1, like binary, or let's say three categories, category 1, category 2, category 3, okay, things like this, then it is called a classification problem. Okay, so when you are trying to divide into categories, so it is another word, categories. Okay, this is a classification problem. If it is numerical value, you are doing a regression problem. Achha. This category, it can be binary or multi-class. So if you have like 0 and 1, two category, we call it a binary classification problem. If you have more than two, we call it a multi-class classification problem. Multi-class classification is a more difficult one, and it requires much strategic approach to tackle. So we'll primarily focus on binary classification for now. And for regression, you have some numerical value, you want to predict some numerical value, that's it. Acha. Now, any question? Okay, so moving on. Now, to actually learn these things, let's say you have this data set previously, you had this data, how can we actually learn something? How the machine learning model can learn something from it and how it can predict? So a very simple one, a very simple approach is there are different algorithms for this kind of task. Okay, machine learning algorithms, ML algorithms. Different algorithms work different way. One of the most common one is called tree-based algorithm. It is very simple to understand. Tree-based algorithm. Achha. What is a tree-based algorithm? Tree-based algorithm works like an if-else condition. Okay. So how if-else condition? For instance, in the house rent example, you can say if like condition, you create tree like if, first example, the number of rooms. Achha, if, okay, the number of rooms is equals to 1, you can say the maximum price should be less than the prediction should be less than 20K. One room house should not have more than 20K price. If the number of rooms is equals to 2, the price can vary from 20K to let's say 25K. If the number of rooms like is equals to 3, the price is like greater than 22K to 30K. So again, number of rooms is 4, then your price is like greater than 30K. So you create a tree like this way, 1, 2, 3, 4, like this, and your tree will go like this way. So when you actually finding a test example like this way, 2, 2, 2, 2 rooms, 2 balcony, so it goes automatically to the second one, it satisfies this one. So the first branch of the tree is telling you that the price of this house should be within 20 to 25K. আমার কথা বোঝা যাচ্ছে?
Yes, sir.
So you create a tree like this, so like a condition based on conditional estimate. So this is, let's say, most important feature. So based on this, you try to create, but it is not giving you very specific. So you can actually increase the branches of the tree. So this is your first branch. Each branch will have some other parameters. Like the second important feature is like the number of, let's say, location. If the location is like, for instance, Uttora 11, 12, 13 like this, the price will be like 18K to 20K. Okay. If this, another if is condition, this becomes another ones. And if the location is like Uttara 10, then the price will be like 15 to 16K. Uttara 10 into price com. Same thing goes for here as well. If the location is like this, the price value is 22K to 25K. If the location is this, the value is around 20K. Same for all those things. So this is like the second branch in your tree. So you take your first one. So this is to then Dhanmondi. So you have to find after this one, go to which one satisfied, which condition is satisfied, go to that condition. Then you can have another condition of number of rooms, number of bathrooms, number of balconies like this way, number of floor, second floor, top floor like this way. This way the tree is created, and your test example will go from one branch to another branch, which one actually perfectly match. Based on this, you actually make the prediction. বোঝা যাচ্ছে আমার কথা? Is it okay?
Yes, sir.
So
Yes,
this
sir.
is like one algorithm, like the tree-based algorithm. It makes prediction like this way. So it works very simple like this, and it can also be like a decision tree. We call it decision tree. It can be a decision tree classifier if it predicts 0 or 1. It can also be a decision tree regressor if it predicts a numerical value. So it's just the output value. If it is like 0 and 1, it becomes a classifier and regression. The same procedure, just the output value is different. Achha. So that is like one classification algorithm like the decision tree. There are other classification algorithms. A very simple one is the nearest neighbor classifier. In the nearest neighbor rule, you have, for instance, in your workspace, you have many features. So it is like 4 dimension, 5 dimension. The number of features is the number of dimension. So if you have 10 features, 10 dimension, let's assume you have 2 dimension for now. You have the values like this. Okay, you have the values like this. And you try to find, let's say this is one test example. You try to find the new, like the nearest neighbors. And based on the nearest neighbors, you find what is the maximum. So out of 5, let's say if it is greater than 3, you say that whatever the highest number of value is, if these 3 is actually saying the output is 1, you will say the output is 1. If the most of them is saying the output is 0, you will say the output is 0. It works like this way. This is the KNN, K nearest neighbor rule. Okay, so these things will be discussed in your class. We are more interested in how to apply it in your practical scenario, how to apply those things in Python. So we'll focus on that one. So there are different classification algorithms like this. So if you have start with something simple, like the logistic regression, this is a classifier, not a regression, although the name is regression. So this is the most simplest one, logistic regression. Then you have support vector machine classifier. Then you have decision tree classifier. You have naive Bayes classifier. Okay. Then you have much more ensemble algorithms like random forest classifier. You have adaptive boosting classifier. More recently, you have XGBoost, extreme gradient boosting classifier. Okay, so these are some of the most commonly used. These are called the traditional classification algorithms. These are more recent, especially the XGBoost is the most recent one, and it actually provides the best performance. XGBoost. You also have other like gradient boosting algorithm, CatBoost. So we'll try to see some of these classification algorithms. Same as the classification algorithm, you have the regression as well. So you have linear regression. So just like you have decision tree classifier, you also have decision tree regressor. Okay, there was KNN. Just like you have KNN classifier, you can also have KNN regression. So both it works both ways. Okay, so that is not an issue. Achha. So these are the different classification algorithms. So different algorithms have different ways of learning. That's why it is actually different ways of learning. Okay, how it is learning. So the decision tree is using like a if-else condition. Support vector machine classifier uses a margin classifier. It creates a margin between the samples. Then KNS classifier uses the nearest neighbor rule. You're familiar with the nearest neighbor rule. So different algorithms have different ways of learning, but the goal is the same, try to predict something. Acha. So we are not interested how these algorithms work in the lab. Okay, that's for your theory part. We're more interested how to apply those things. Acha. And to apply these things, we'll rely on a particular library that is called scikit-learn. Okay, its pronunciation is scikit-learn. In short, we call it sklearn. This is the most widely used library for like a machine learning algorithm if you want to design, and there are different other libraries for different tasks, and those things are actually built on top of the scikit-learn library. Okay, and very much flexible. So for instance, here when you are working with other like imbalanced data, we'll see later. So we have a library that is called IMBlearn. Okay, for imbalanced learning. For XGBoost algorithm, you will find a XGBoost library. Okay, that is also similar to scikit-learn implementation. These things actually work very simple. So you also have scikit-genetic, I think, if you want to apply genetic algorithms. So there are different optimization algorithms we'll see. So we'll focus on scikit-learn library for now. Okay, any questions so far? Any question? Achha. So let's start working with our lab. So today, I believe you already understand these things. So we start working with a data set. Okay, we'll start working with the same data set that we have seen before. In the last lab, we have seen the titering data set on which you actually perform the ETN. So we'll use the same data set as well. In the titering data set, the prediction column was survival, whether a particular passenger survived or not, 0 and 1. So this was a classification problem. So we'll try to work on this one. We'll try to learn from the data that what is the chance of a particular passenger survive or not. Then we are going to try to predict on some other data sets. Okay. Acha. To do that, if you actually go to your can you see the screen?
Yes, sir.
Acha. So first of all, you start with the libraries. So these are the very common libraries. You need pandas, numpy, so. And from the scikit-learn module, we have to import some special things. Scikit-learn is a very large library, so you don't have to import everything. Import some of the basic one. And if we use this asterisk sign, we can actually import every function within this particular section, particular module. So for instance, we are using preprocessing. We have to preprocess the data. So from scikit-learn.preprocessing, I'm importing everything. Okay, I can import every one of them one by one, but it is better to import everything for now, just for simplicity. Then also for model design, I need model selection. Okay, then metrics for performance measures, I need metrics. So from scikit-learn metrics, I'm importing everything. And for imputation, you have seen machine data handling, we have to work on the last lab. So input for scikit-learn input, I'm importing everything for now. Achha. These are the different libraries we'll need to build the model. And as for the classifier, you can see from linear model, you have the logistic regression classifier. From SVM, you have SVC, support vector classifier. Okay. Then Gaussian MBDR, these are different classification algorithms. So from every one of them, we have imported those classification algorithms for our task. Okay. Achha. Now you have the data set, some very common thing. So you have the original data set that you have. You are already familiar with the data set, so I'm not going to discuss much. So you can see the data set size is 891. Okay, 891 samples, and there are 12 columns. Okay, out of the 12 columns, there is one column that is the target. So you have actually 11 features. Okay, so target variable is the last one. So you separate it when you have the data. So start working. First of all, feature and target. What you do, you separate the target. So usually what you do, x is equals to your features and y is the target. So you know the drop function, data.drop. Okay. Let's say just data dot, what is the one, survived, I think. This will take the survive column in your y, and you can just drop the survive column, data.drop and survive data dot. So that will actually, all the features will be on x, and the other features will be on Y. This is something we start. On the start, we divide the data set into features and the target one. That is your step one. Okay, and that is being done here. You can see this is the target column. Okay, and you have 0. There are 549 instances where the passenger did not survive, and 342 where the passenger survived. Okay, acha. Acha, and these are the feature variables. You drop the survive column, so the remaining ones is your feature, and these are the column names. Acha. So when you have the data, you have seen some of the EDA. EDA, the purpose of EDA was to understand what is the distribution of different features. This is the first step you should perform whenever you are working with a new data set. You should first try to understand the data very carefully. Okay, it is most important task. Okay, whenever you have a new data set, first try to understand the data, what that data represent. That's the first step. Then you go for next and next steps. So you are already familiar with EDAs in the last lab, so you already know what are different things. So after you have the data, X and Y, we know that there are some issues in the data set. Previously, we have seen. So similar, based on that understanding, we know some of the features may be unnecessary. So that is the first step. You have to remove some of the features. Okay. What features do we remove? That is the features that are actually unrelated or does not hold any value. For instance, there was the name column. Okay, name does not actually hold any significance to the prediction. Okay, that is not related to the prediction type. So name is not, or passenger ID. This is just a sample ID, just like with student ID. Student ID does not hold any specific information. Okay, just a number. So these things you don't need. So you have to remove these features from your machine learning model. Otherwise, your machine learning model will try to learn something unnecessary or unrelated, and that is not going to give you good performance. So you remove names, things like this, passenger ID. There is another one issue, like if you have some values are too many missing entries, okay, too many missing entries, then that column should be removed. Okay, so previously you have seen in this, when you did EDA, there are some 1 or 2 particular features where there are too many missing entries, so we can actually remove those features, okay, that have too many missing entries. So another thing is, like, if you have redundant features, redundant means correlation. So correlation is almost close to, correlation between two features is almost like greater than 95%, 0.95. Okay, so if the two features are very highly correlated, then you can actually remove one particular feature. You have seen this one in the second example. There are some features that are highly correlated, just complete duplicate. So you should remove that features. But in our Titanic dataset, we didn't find any redundant features. So we can actually remove, we don't have to remove anything. So if you come back here in the remove features, as you can see, the cabin feature has 687, more than 50%. So we can actually remove these cabin features. But age is 179, we can impute the value. Okay, so we don't have to remove the age features, but we have to remove the cabin feature. So as you can see, drop columns. I am dropping the passenger ID, I am dropping the name. The ticket is just a number. So I am removing this one as well as the cabin. So I'm removing those features. So from X, these things are removed. Just drop the features. You know how to drop some features from the pandas library. So those things are done. Now, so this is the second step. Once you have these things, you drop some of the features that are unrelated or missing entries, too many in these things. Number 3, some pre-processing memory required. Pre-processing is like, for instance, so if you have something in the categorical format, like for instance, male and female, if you have male and female, it is better to convert it into numerical value. Because as you can see, there are different machine learning algorithms. Some of them can only work with numerical value, cannot work with string value. Your random forest classifier or decision tree, they can work with string value. Okay, categorical string is categorical string. But other values like support vector machine, they actually rely on numerical computation, okay, or naive bias. So for those things, you need to convert the categorical into numerical. So you just convert it male and female to 0 and 1, 1 and 2, whatever you prefer. Okay, just convert it into some numerical value. You have done it in the previous lab. We can just use map or other functions. So like this way, you have two features here. As you can see, male and female, and the invert column, you have SC. There are three different types. So you can actually map this to numerical values 0 and 1 like this way, 0 and 1. Okay, as well as the invert one, you can map it to 0 and 1 and 2, or 1, 2, 3, whatever you prefer, you can do it. Okay. Any questions so far? Any question?
No, sir.
Okay. So, so whenever you have this kind of like categorical value, just try to convert it. Now, if you have like too many categorical values, like 5 or 6 or 7 types, you can actually, there are other functions that you have seen in the previous lab. There are other functions instead of map. You can use those things, just like label encoding. You can use for this purpose. For this purpose, you can use map or label encoding to encode those things to particular values. Achha. There is another one that is called one-hot encoding. For some machine learning algorithms, one-hot encoding is better. But the problem with one-hot encoding is that it increases the size of the features. So if you have 6 categories in one feature, one-hot encoding will convert it into 6 columns. So for now, you just ignore the one-hot encoding for now. Okay, because classification algorithms like random forest, they work very well. They work without one-hot encoding. So you can focus on just map and label encoding for now. But if you try to see some of the like Kaggle practice, you will always find this one. Just why I am just mentioning, but you can ignore it for now. There should not be much difference in the performance. So that is the pre-processing step. If your data is in some string values, you should convert it into some numerical value. Achha. Any question? Okay. Now, number 3 is done. So these are some of the steps. Like if you try to draw a pipeline, like the data you have. So first we actually split into X and Y, then remove features. It comes to remove features. Okay. Also remove rows. For this one particular, we did not remove any rows, but it can happen that if particular row actually has too many missing columns, like a particular row has, let's say, out of 15, out of 12, 10 features is missing for a particular row, then you should remove that row. Okay, it goes both ways, both features and the rows. But you should first look at the features first, then you should look at the rows first. If a particular feature, the same concept, greater than 50%. Okay, it is not here in this Titanic dataset, but the assignment that I will give you, you will find this scenario. But some of the rows have too many missing entries. Okay, so you don't need to remove the features, rather you should remove the rows. You should look into that one. But you should be more extra careful when removing rows, because we don't want to reduce the size of the data set. So you only do it when you have too many missing entries, let's say greater than 75 or 80%. Only that scenario, you remove the rows as well. Otherwise, you can keep it. Yeah. That is one task. Remove features, then some pre-processing. Pre-processing task এর মধ্যে পড়ে হচ্ছে like numerical value. Everything should be numerical, like this way. Okay. Acha. So after this one, before moving forward, you should divide the data. This is called train test split. Okay, this is called train test split. Okay. Acha. Why do we perform train test split? As you Acha. Let's say you have the data like this. What you want to do, you want to train on certain portion, let's say 80% of the data. You want to test how your model is performing on rest 20% of the data, so that you can understand how your model is working. That's why we perform this kind of train test split. Split the data into training part and testing part. Now, the most common way is to divide it into 80 by 20, 80:20 ratio. So it can be 70:30, that is also fine. But normally we perform this 80-20 split. Okay, so you train your model on this portion, and this is like your unseen. You consider this portion as unseen. although you know the result, you have the result with you, you don't know, you have the result for testing, but you will not, machine learning model will not have any information of this portion. This is only for testing your model. This is the thing that is actually known to your model, and you will train your model on this portion. Is it okay? Any question? Any question?
No, sir.
Acha. So there is one issue like testing. Acha. One is called internal validation. Internal validation. Another is called external validation. So you see, whatever the data you have, you are testing it on a portion of the data. That is called internal validation. So the data set that you have collected here, you are testing on a portion of that same data set. That's why it is called internal validation. But sometimes, especially when you are actually applying your model in some real world scenario, you also want to perform external validation. External validation is like, for instance, let's say you are designing a computer vision model for, let's say, like vehicle type. Okay. On a street, you have collected some video or data. You want to predict the vehicle like bus, train, then bike, things like this. So you take your data, you train your data and test your model on your data set. But it is better to perform the validation. You have trained model, then test it on some other data source, not from your PC, not from your camera, but from other camera. Okay, other camera taken by some other person. Test it from some other area on which data the model was not trained. That is called external validation. That is much more reliable. Okay, that is much more reliable. You want reliability. So that is why you, when it comes to the concept of reliability, you work into those parts. Okay. So that is the concept external validation. But for now, at this stage, you may not have the data for external validation, but when you go for like practical implementation of a particular system, you definitely should rely on external validation. You should test your model some external data set to see whether your model is actually doing good. Okay. But for your learning purpose, most of the cases will rely on internal validation for now. Okay. Any question? Are কোনো question?
No, sir.
Okay. So let's come back here. So what we are going to do now, after you have your data set, you have this X and Y, remove features and other things and pre-processing, you have to split your data into train test split. So to do that, you have a function in your scikit-learn library that is called train test split. Very simple. In the train test split, your code works like this way, like X train, Y train, a comma, X test, Y test, like this way. Okay. Four output variables. So the function is like train test split. The function is in the data preprocessing, the library that we have imported from the scikit-learn. We have already imported everything from that particular library, so we don't have to call scikit-learn dot preprocessing dot like this. So we can do it directly. So train test split, you put your X and Y, something that you have already divided, X and Y. So place it here, X and Y. Then you can actually define the size. Okay, the test size, you define it as a ratio of 0.8, for instance. Sorry, test size is 0.2. Sorry, it should be 0.2. Okay, so there is a particular parameter that is called random state. Okay, and it can be any number. So you should actually add a number from here. So the purpose of the random state is that if you replicate it, like you have run your code for today and you are done. If you use the same random state, the division will be the same. Whatever the sample was in the X train, the same samples will go in the X train. But if you change the random state, different samples will be there. আমার কথা বোঝা যাচ্ছে?
Sir, can you repeat this part?
Random state is to replicate your example. So this process like randomly splits the value from X and Y. It will split the value. You have X and Y. Split some of the value to train, some of the value to test. Okay. Now, if you try to do it again, let's say for again, the same values will not go to train and test, different value, because the process is random. But if you want to keep it the same, like whatever the value that was in your train, you want the same value in the train and test, you should have to fix a random state. If you make it 100, as long as you keep your random state 100, same values will go to train and the same values will go to test. If you change it to, let's say, 200, different values will be on train, different values will be on test. বোঝা যাচ্ছে আমার কথা এখন?
Yes, sir.
So, different
Yes, sir.
random state will allow you to, you will actually make the variation, there will be there different variation, split will be there. It will be split into different segments. Acha. So if you keep your random state fixed, you will have the same data set. So this is important to replicate. Otherwise, what will happen? Say, let's say today you are running your model, you are getting an accuracy like 80%. Tomorrow you are running with a different random state, you will find the accuracy is 78%. So any machine learning algorithm is much more stochastic in nature. Okay, stochastic means in different runs it will give you different performance. Okay, so if you run the same random state, it will give you the same result. Okay, so that's why it is important to fix the random state. Always do it. So this is your train test split. You have x and y test size 0.2. You can make it 0.25 or 3 if you want to increase. Usually for a small data set, we use 0.2. Okay, and the random state like this way. Train test. So this is your X train. Now you can see you have 712 rows in the training data, and the testing data you have 179 rows.
Sir,
Follow?
sir, does the number we have chosen for random state, does it hold any significance?
No, just a random
Like
number.
10 or 100 or
No,
200?
nothing. Just a number.
Okay.
Same number, same. Otherwise, different number, different. You can use any number. The value does not mean anything. Okay. Any? Yes, 236. Acha. So now you can see your training data have now split it into, your original data has been split into train and test. There are 712 rows. That means we are going to learn from this one, or train your model on this one, and test your model on the remaining 179. Okay, so the performance will test on the 179. Okay, any question for now? So
Are these 179 rows that have been chosen for being tested, are they getting chosen randomly, or is there a criteria
randomly,
for choosing the random?
they are chosen randomly. The data is divided randomly. Okay. Acha. So as you can see now, after we have done this portion, so now you have the train data, and on this side you have the test data. Okay, on one side you have the train data, on the other side you have the test data. So train, test. Now, as you can understand, test data means something you don't have any information of. You don't have any statistical information on any other thing. So everything that you do, you should do it on the training data. No information of the test data is available to you. Okay, so you will progress, we will actually proceed on that way. Achha, let's see how do you proceed. After this part, okay, comes the imputation. Previously you had like missing entries in the data. Okay, and you have seen, we have discussed how to perform imputation. That means we have to replace some of the missing entries. Achha. There are there are some simple ways, like using the mean value or the median value. That is one way to impute. There are some multivariate regression like mice algorithm. You can use any one of them. For here, we have used the mean option. Okay, and you know how to perform imputer. You create object, the simple imputer, the imputer object, then you apply it. But when you apply it, there is a scenario. You create an imputer object. You create your imputer object, then you feed the object on the train data. That means it is going to fit, means it is going to learn from the training data. So let's say it is going to learn the average of a particular column. For instance, the S column was missing. So average of the S column, it is learned from the training data. After fit, you transform the train data. That means transform means it is going to replace the missing values, replace missing with the average value that you was learned. Replace missing with the average one that you have learned. After this one, you only transform the test data. That means it is going to replace all the missing entries on the test data, with the average value that was learned from the trained data average. Because you don't know the average of the test data. So you cannot know that. Because test data is coming one after another. The statistical information is not available. So you should be very careful here. So you only fit on the training data and transform your trained data based on that. You transform your test data based on what you have learned from the trained data. So this was discussed in the previous lab as well. So I should not be any issue. So as you can see, this is the imputer I have created. And so I have fit the model on this one, X-train. We have fit it on here. Then I actually transform the X-train. Imputer.fit transform, I transform the training data. Then I'm transforming the test data, not fitting it, just transform it. Okay, this way. So this you can actually then you have the column like this way. So same number of rows and same number of columns, but the imputer object has now fitted it. So that means there are no missing entries here in the training and test data. Is it okay? Any question? So
স্যার
হ্যাঁ বলো।
স্যার সবসময় কি অ্যাভারেজ ভ্যালু দিয়ে ইমপিউট করা উচিত যে কোনো
না,
মিসিং
না।
ভ্যালু একটা কলামের?
না। আচ্ছা। এটা হচ্ছে তোমার হচ্ছে ডাটার টাইপের উপর ডিপেন্ড করে। ইউ সি when you have values like numerical values, like for instance age is a numerical value. Here you can actually, if you have a small number of missing entries, you can use average one, the mean value. If you have categorical value, then you should use the mode, that is the most frequent one, not the average one. Okay, I'm doing the average one for simplicity. The best one, it is both of these things are univariate approach. The better one is the multivariate approach. So when you are using on like a practical model or like your project, you should definitely work on something multivariate. So mice algorithm works the best for this one. So when you are working on, if your data is like 3 or 4 mice algorithm, the same thing. So you should work mice algorithm for this kind of imputation. That is the better one. But if you have like 5 to 10, very small number, you have 2000 data set, out of them 5 or 10 entries are missing. For this one, you can actually work for univariate approach. But you have like 100 missing out of 2000. In that scenario, you should definitely work for multivariate approach, mice. Okay. Is it okay?
ইয়েস স্যার।
Achha. So this is your imputation. So imputation and fit here. You also perform imputation, but this is separate because you are doing imputation, but only transforming it, not fitting. After imputation comes the scaling part. There are different algorithms, like for instance, regression models, linear regression or logistic regression. They are susceptible to scaling of the features. Like if one feature value is 0 and 1, another feature value is 10,000, 20,000, the regression model has some difficulty learning properly. So all the features should be in the same scale. Okay. Now again, this issue is particularly for logistic regression, okay, or KNN, for instance. This is very important. But there are other algorithms like decision tree or random forest. This is not very important. Random forest can work with the different value strengths. That is not a problem. But in general, I am trying to show you the general way. In general, it is better to perform scaling. Okay, that's why we are going to scale the data. When you scale the data, there should not be no issues. But especially for random forest, there can be a small performance difference, but that should not be a major issue. So it is better to scale your data whenever you have. And for scaling, there are two ways. One is min-max scaling. Another one is standard scaling. So in min-max scaling, you convert every value to -1 to +1 range. So every column, it works like column-wise. Everything works column-wise. So whatever the particular column, let's say for the age one, for the age column, whatever the minimum value of the age, you make it -1. Whatever the maximum value of the age, you make it +1. And rest of the value is divided into this ratio. বোঝা গেছে আমার কথা? Similarly, let's
Yes,
say
sir.
another one, like let's say fair. whatever the minimum fare, it becomes -1. Whatever the maximum fare, that becomes +1. Everyone comes within this range. That's the scaling part. And this way you actually scale each of the feature. As for the standard scaling, that you calculate the Z-score. Z-score is the mu, the value x minus the average of the column divided by standard deviation. So the range is like within 0 to 1 most of the time. Okay, that is the standard deviation. It follows the normal pattern. Acha. And as for the scaling part, it actually also works in the same way. For scaling, you should fit on your model and the training data. You have to also do the scaling on the test data, but you only transform. Okay, don't fit it, just transform it, because you don't know this again. You don't know the range of the test data value. So you should fit it on the training data. So similarly, if you come here, that is the normalization. Scaling means normalization. So I have used the standard scalar, that is the standard scaling Z-score. You also have min max scalar. You can also try this one. There should not be much difference in the performance. So you fit it. As you can see, I am fitting it on the train data. Then you have the standard scalar object. Then you have the transforming it on the train data, also transforming the test data. So you can see all the values now becomes minus and plus. Okay, you can see the values are becoming like this way. Within the range of -1 to 1, all the values are coming in this way. So now you don't have the specific information what is the actual value. Okay, so as you can see, the values are now transformed. So here is one issue you can ask, that for instance, the gender column. Should I actually scale the gender column? বলো, করা উচিত কি করা উচিত না?
উচিত না, I guess.
হ্যাঁ, so when you have categorical values, you should not actually do this like scaling on the categorical values, because category values are 0 and 1 and 2. These are like specific values. So scaling should be only for numerical values. But in general, like for generalization, if you have 1 or 2 features that are actually categorical, this is one of the issue working with the tabular data. Okay, you have to take care of different types of data, numerical data, categorical data, ordinal data, things like that. So if you do scaling, it is not going to harm your performance significantly. Okay, that's the thing. It is better, again, it is not going to harm your performance significantly, because even if you have 0 and 1, when you are scaling, it is not going to changing much. But standard approach, like the standard way, standard thing is to not to perform scaling for the categorical value. But if you do it, it is not going to cause much harm. So I am going to show you how to do it. Okay, so I am doing it all the rows. Otherwise, what you have to do, you have to like separate the features that are numerical, perform scaling, then just append the features that are categorical like this way. So that is just give you more step to write, but it is not going to be much different. Is it okay? আমার কথা
Yes,
বোঝা
sir.
যাচ্ছে? আচ্ছা,
Yes, sir.
Yes.
so that is your scaling part. So everything is the entire pipeline is coded here. So if you want to replicate it, it should not be very much problem now. Okay, any machine learning model, whatever you try to do, it should follow it in the same pipeline. Okay, so এটা গেল. So we have done with this one. So we have done up to this portion. So I have started with the data, perform some pre-processing, then I have train test split. And before go for training, you should perform this kind of imputation and scaling. Okay, after this portion, your model is now fit for training. So now you train your model here. So this is called fitting your model. On the train data, you train your model. Okay, then you will test on this one or predict on this one. Achha. Now to train your model, as you can see, you first define the classifiers. Achha, let me share something. So if we come here, can you see the screen? এটা দেখা যাচ্ছে স্ক্রিনটা?
Yes, sir.
Yes, sir. Yes, sir.
Achha, so as you can see, this is the support vector machine classifier, and there are many different parameters inside. Okay, so each and every classifier that you see, you will find many different parameters inside. for now, you don't need to worry about those things much. There are, in the next lab, we'll see some of the parameters, the importance of some of the parameters. So if you have studied support vector machine কি পড়াইছিল ক্লাসে পড়াইছিল?
No, sir. এখনো
No,
পড়া
sir.
হয়নি।
আচ্ছা, so there are certain things like, for instance, one important parameter of the support vector machine classifier is called a kernel. The kernel can be a linear kernel. That means it is going to divide a linear line between the instances. But you can see here it is radial basis function, RBF kernel. So this is a little bit different. So this is for when your data set cannot be linearly separated. So these things are important. So there is something that is called hyperparameter tuning. We try different kernels. So that is something we are going to discuss in the next lab. For now, we are going to work with the default setting. Okay. For today's lab. So you don't have to worry about these things for now, but next lab we are going to see some of the features. So these are the features, so every classification algorithms you will find many different, especially if you go for random forest classifier. So in the random forest classifier, you will see there are many different, the number of estimators. Estimator means the number of trees. Okay. You combine 100 different trees, that's why it is called a forest. Okay, that's why it is called a random forest. There are randomization inside. And then the Gini criterion. So there are many different features inside, and each of them have some particular purpose. So for now, however, we are going to ignore those things, and they have actually have the default value set so that you can work directly. So you can see the default value is 100. So it is just 100 for now. Okay, we are working with the default values for now. Later in the next lab, we will see how to actually tune those values in particular. Any question? কারো কোনো question? আচ্ছা, so let's come here. So what you do first, you like define your classification object, just like an object, like you have created the imputer object, you define your classification object, like the k nearest neighbor object. So you see the number of neighbors I have said it is 5. I think the default value is also 5. Okay, so this is very important parameter for the k nearest neighbor rule. If you use n equals to 10, the performance will vary a lot. Okay, in the next lab we'll see. And n jobs, you see n jobs means, you see, if you want to do something faster, if you want to, especially random forest like this, when you want to do it faster, you should use n jobs. N jobs means it is performing parallel operation in your computer processor. It allows to perform parallel processing when you actually make n jobs equals to -1. All the processors will be used simultaneously. Okay, you have like 8 core or 16 core inside. All of them will be used parallelly when you use n jobs equals to -1. So when you have like computational heavy, very large data set, 100,000 instances, then you should actually use these things. Acha. So we are defining the classifiers. KNN classifier, logistic regression classifier. So DT classifier, you see in the DT classifier, I used a random state, because if I don't use the same random state, it will be different. But I think logistic regression, the classification function is like this way. You don't have any random state. Acha. So galo. So what do we do? Let's say fit knn.fit. I just feed the model on the train data, X train and Y train. So the code is very simple here. So you define your models like this. Let's say KNN is defined like KNN classifier, blah, blah, blah. SVC is defined as support vector machine classifier like this. Then knn.fit, you fit on your X train, something that you have already, X train and Y train, something you have already divided in the previous system, train DS split. So you fit your model here. So model is fitted, that means model has learned something. Okay, then you try to predict. Okay, so you see after this one, I am using knn.score. That means it is going to give you how well it can actually fit on the data. Based on those things, how well it can fit. You can see the accuracy at 86%. That means, let me come here. So if you use knn.score, by default, it is giving you the accuracy, the training accuracy. It is giving you the training accuracy. So 85% means 85% of the samples were predicted correctly when it was training the model. Okay, it could predict correctly based on this concept, based on this one. Okay, and when this is for training. If you do the same for testing, X test, Y test, KNN score. ঠিক আছে, and you can see the prediction is 83%, very close. That means whatever it was learned in the training data KNN, for the training purpose it was very close 86%, for the testing it was very close 83%. Same thing if I try to do it for logistic regression, when you fit on the training data and test the performance, you can see training performance 79%, it is a little bit lower, you know, and the testing performance was 82. On the test data set it performed better. For decision tree you can see training performance was 98%, দেখা যাচ্ছে?
Yes, sir.
So when you are fitting the decision tree classifier, when you're training accuracy is 98%. That means when the model was training, you are very successful in learning whatever the parameters are. Okay. But when you test the model, same thing, the performance has now dropped to 75%. That means the model that you have fitted, it was working very well on the training data, but it was performing very poorly on the test data set. বোঝা যাচ্ছে আমার কথা?
Yes, sir.
So this is what you are actually trying to do after this step. When your data is ready, you train and test. So you train your model and you test your model and see the performance. For now, there are different performance measures. For now, we are focusing on accuracy. Okay. So accuracy is the most common metric. There are other metrics we'll learn in the next lab. We are focusing on accuracy for now. When you have a regression problem, you should focus on, let's say, squared error, mean squared error, or R squared, things like that. So there is one concept of overfitting. এটা কি পড়ানো হয়েছিল? Overfitting, underfitting.
Yes, sir.
Okay. So this is a very important concept in your model. So as you can see in the decision tree, the training accuracy was 98%, testing accuracy was 77%. So model কি হচ্ছে? Overfitting হচ্ছে আর underfitting হচ্ছে?
Overfitting
Overfitting.
হচ্ছে।
এটা হচ্ছে overfitting হচ্ছে because it is learning very well. It can learn very well on the training data, but it is not learning well in the testing data. This happens in the decision tree classifier when I am using the default parameter values. Okay, in the default parameter settings, the decision tree can grow very large. And when you create a very large tree, your model becomes overfitted. There is a process that is called pruning. So you can use pruning to avoid this kind of overfitting. So that is another issue for not for now, not for today, not for the lab, it's theory. But if you look at the SVM classifier, the performance was like 84%, 83%. This is not overfitting. So this is working well. Okay. বোঝা যাচ্ছে আমার কথা? So
Yes, sir.
you can actually test your model's performance like this way and see how different models are actually working. Overall performance. And you can also test your individual prediction, like this is your X test. This is the second test example that you had. These are the values, these are the values. And you can see there is a function .predict. So you have the KNN that is fitted on the data. And if you predict it, you can see the prediction is 0. Okay. Original value y test, we already know the value was 0. Y test ilog was 0, like this. So when you are predicting it here, it is also giving you 0. That means the prediction is actually correct from the KNN classifier. So you can also check individual prediction like this way. If you look the same thing for logistic regression, you can see it is giving you an array. Why it is giving you an array? 0.84 and 0.15. What is this? এটা কি জিনিস? Anyone? Anyone?
The probability of 0 and probability of 1.
Yes. Logistic regression actually works on probability. KNN works on 0 and 1 directly, but logistic regression works on probability. So it outputs the probability of something. So the probability of 0 is 84%. That's why the output is 0. So we use like the boundary as 0.5. It is higher than 0.5. We make it like we take it that way. So you can see the predicted probability is 0.84. Okay. Similarly for decision tree, the predicted is 1 like this. And X test for support vector machine classifier 0. Acha. Now this is also done. So your home task will be class task. You don't have to do it now. In the home task, you have to use different random state. This is what you did in a particular random state. If you change the random state during the train test split and see how the performance varies. I worked on 100. So when you are actually working at your replicating these things, Just change the random state and see how if you are getting the same performance. You should get different performance when you use a different random state. Is it okay? Is it okay?
Yes, sir.
Acha.
Yes, sir.
Now, this is the so far. So this is actually the entire machine learning pipeline that we have discussed so far. So if I just make it summarize, you start with the data set. You start with the data set. You start with the data set. You have your X and Y. You remove features. You pre-process your data. You train test split. You impute your model. Scale. Impute your data. Scale your data. Then fit. Then make prediction. Okay. Acha. So this is one way to do it, and this is the standard way for you to learn. There are other ways to do it much more easier. One of the thing is called using pipeline. Pipeline is a function that you can actually use to perform everything is in a much more standard way. What you do, you create a pipeline object. Okay, it is like a list, and you say inside the list you say what you want to do step by step. So let's say first, let's come here. So you see scikit-learn.pipeline, I have imported the pipeline, and inside the pipeline you can see I've defined it. First, I want to define, this is after your XY. Pipeline comes after your train test split. Before train test split is there, that is the pre-processing. After train test split, you can use a pipeline for rest of the part. So simple imputer, the imputation, then standard scalar, then fitting the model. If you put it inside a pipeline, it is going to do everything directly. You don't have to do it step by step. You can do everything directly if you put everything inside the pipeline. বোঝা যাচ্ছে আমার কথা? This makes the task much more easier for you. Okay, I have shown it. I have not shown it before because you should learn how to do it one by one. But especially when you are trying to train your model later for your project or things like that, you can use the pipeline. It makes it very simple. You can see the input is a array, and the serial you have to maintain. If you it will perform everything, perform the operation serially. So whatever your X and Y was, okay, so this is your pipeline. After this one, you actually fit your pipeline. So after you have defined your pipeline, you just do it like this way: pipeline.fit X comma Y, X train comma Y train. So after you do this, okay, so this is the object, pipeline object you have created when you try to fit it, because you see, we have fit all these things. This was, all of them were fitting. If we come here, this was fit, this was fitting, we are actually fitting it. So all the fit, you can actually put everything inside the pipeline. It works like this way. So if we come here, so you have the pipeline. So this is the pipeline object. When you fit it, it is going to fit on the training data. So first you perform the, let's say the imputation perform. So it will perform the imputation on X train, Y train. Then on the imputed data, it is going to perform the scaling. Then on the scale data, it is going to perform the training. So this way it works this way. Is it okay?
Sir, why we are not using dot fit transform here?
No, I'm just when you're using fitting, it is going to fit on your model and transform directly. It is inside, inherent. You don't have to write transform here. So when you
Sir,
are
it is for the pipeline
it is
part
only for the
only.
pipeline, because it is going to, by default, it is going to do it inside. You don't have to worry about it. Okay.
Okay, sir.
Acha. Last thing. So this is a much more way. Acha. Last portion. Acha. So last portion is your cross validation. So in the previously we have done train test split. That is like, if you have 80%, I have trained your model on 80% of the data and test on the 20%, right? And that's why I'm making the prediction. But what if, let's say, but we are not testing on the entire data set. We are only testing on a particular portion of the data set. That is also random. If I change the random state, you're going to get a different performance, because this 20% will be a little bit different. So based on this, the performance will vary significantly. So due to the stochastic nature, let's say in one run, you are getting performance 80%. In another run, you are getting performance of 70%. Another run, suddenly 85%. So which one should you take? Okay, based on this distribution, how it is split into 80 and 20, you can actually have different ones. Let's say if the training is very good, you will get a very good performance. If the test data is much more complicated, you will get low performance. So this kind of variation is not something we actually we want. We want a very static performance. So the solution to this one is cross validation, performing cross validation. So if you do the class task, that is a random state fixed or random state and test it, you will see different performance here. So to avoid those things, we perform something that is called cross validation. What is cross validation? Let's say you have your data. I divide the data into 5 folds, A, B, C, D, and E. What do? You do 5 runs. You train your model on A, B, C, D and test on E, and you take the performance. On the second run, you train your model on A, C, D, E and test on B and take the performance. Then A, B, D, E, B and test on C, then take the performance. So you do it 5 times and take the average. That average, that means you have now tested on each portion of the data set. You have tested on every data that you have. Internal validation, but you have tested on every portion of the data set. So that gives you a much more stable result. So that is called the cross validation. আমার কথা বোঝা যাচ্ছে? Are you getting me?
Yes, sir.
Yes, sir.
So this process is called cross validation, and this gives you much more stable performance measures. So this is what we actually use. Okay, especially when you have tabular data, a small data. When you have a small data, we use this kind of cross validation always. If you have a very large data set, then cross validation can be difficult, can be time consuming, because you are training your model now, let's say 5 times. Instead of 1 time, you're training your model 5 times. So then the computation time will be very large. So very large data set, we perform train test split. Okay. But if you have a small data set, definitely cross validation. Acha. As for cross validation, this is called k-fold cross validation. The k value can be 5 or 10. When you're dividing into 5 different folds, this is called 5-fold. If you divide it instead of 5, 10 folds, then it will call 10-fold cross validation, where you will train on 9 folds, test on the remaining fold, like this way. So this is k-fold cross validation. Is it okay?
Yes, sir.
Acha. So a much better version of this one, it is called a stratified cross validation. A stratified k-fold cross validation. Why stratified? Stratified means, let's say the imbalance ratio in the data set was 1:7. That means number of 0 was a number of 1 difference is 7 times more values. So to maintain this ratio in every train test split, you perform a stratified. If you don't maintain the ratio, it can happen that in one of the cases, all the test values are 1. There were no samples from 0 available. It can happen, especially in imbalance ratio, when the imbalance ratio is very high. We'll look into it in the later labs. So for now, you just know that there is another one that is called a stratified cross validation. A much better one, much more stable. This is like more stable performance. We want much better stable performance. Stable performance, and there is a measure called standard deviation between the performance you have. We want minimum standard deviation. Okay, so the different accuracy that you're getting, like 80%, then 90%, that is like standard deviation is very high, but we want closer. So 80%, 81%, we want it very small. So that's why that is another measure. So a much better one is called repeated stratified cross validation, k-fold cross validation. That is, it will perform stratified, then it will repeat the process using different random state 3 times or 5 times, like this way. Or if you want much more stable, you can use 50 times. Okay, so these are the 3 different types of cross validation. If I look into our data set, you can see I'm using cross validation k-fold. So there is a function that is called cross validate. Okay, I have the pipeline that I have just defined, X and Y. You put everything inside cross validation, it will take care of the result. You don't have to separately train or fit anything like this. When you perform this cross validation, the cross validate function here, the cross validate function will do it for you. So you have this cross validate. Okay, you have your pipeline that you have your X and Y, and you define the 10K value. If you, and there should be, I think, random state is also there, take care of the random state as well. If k is equals to 10, it is going to perform 10-fold cross validation. Okay, so you can also check the other types of cross validation, repeated, stratified as well. So if you do it, when I'm doing this 10-fold cross validation, CV is equals to 10. Okay, not k, CV. So as you can see, this is the fit time, this is the score, and this is the test score. You are getting the 10 different folds. You see, on the first fold, it is getting 77%. Second fold, 76. Third fold, 74. Fourth fold, 83. The average of all these things, that is what you want. So the average result, so if you take the average of it, figure if you take the mean of it, so take the average one, you can see the mean score is 78%. So this is the average cross validation result. So this is when you are using this cross validation result, that is the test score for all different folds. So it is no longer you are not measuring overfitting anymore, because you are just taking the performance. So that is the standard performance. So average score is 78% now. So that's the performance from your Gauss regression, whatever you are using. And from what is decision tree, the average performance is like 79%. Okay, your training model may be overfit, but when you are doing this, you may not understand whether your model is fitting or overfitting or not. So first you should check whether your model is overfitting or not to tune your parameters. Then you should go for cross validation to get the ultimate results from all the data set. So that's your cross validation. Is it okay?
Sir, in case of cross validation, that means there are no training and testing scores separately.
Yeah.
Okay.
So all the cross validation, you are only seeing the test results. Okay. And you're taking the average of the test results. Okay. Acha. Any question so far?
Sir,
Bolo.
while using the pipeline, we are using IMP for simple imputer. In the IMP, previously we have used the strategy as mean. So are that mean is implementing in this pipeline?
Yeah, simple imputer. I'm defining simple. This is the name. IMP is the name I am using. This is a string. This is nothing actually. You can use anything, IMP. This is the string just to call it if I need it, something like this. If I
Sir, IMP object যখন আগে ক্রিয়েট করছে তখন ওখানে স্ট্র্যাটেজিটা হচ্ছে মিন হিসাবে নিছে, মানে ওটা তো আমরা মোড হিসাবেও নিতে পারতাম। তো এখানে যখন আমি পাইপলাইনের ভিতরে
অবজেক্টটা এখানে আমি ইউজ করতেছি না, এই নামটা ইম্প অবজেক্ট না, আমি এখানে আলাদা করে জাস্ট সিম্পল ইম্পিউটার অবজেক্ট এখানে ডিফাইন করা হচ্ছে। The imp object that is created, we don't need it for pipeline. We don't have to create a separate object for simple imputer. This is just the name I am using. Okay, this is the object, simple imputer. Inside the default is mean already. You can change the inside, whatever you want to do inside here. You don't have to do it separately. What I say?
Yes, sir.
Okay, so a scalar, I am just using a standard scalar here. Anything you want to define, you are defining here. You don't have to define it separately. Previously, I defined as SC or something like this. The first one that I'm writing here, a scalar, that is actually just the name of this one. So if I try to put a graph, you can actually put a graph. The name will come as a scalar like this. Okay, you can use any other thing. For instance, I'm using LR to name it. When I try to create a graph, I should name it as logistic regression, that the graph will be much more clear. That's why you have the name. It does not have any other value. This is the object that I'm creating, LR. But here you can see LR, I am not creating an object here. I'm using the previous object that I created. These two are the object I have created. LR is the something that I have created earlier. So you just actually do it by yourself. You can define it here. You can define it previously. Both will do. That's fine. Okay.
Yes, sir.
Any other question? Acha. So this is your machine learning. I believe you should have no problem in creating a machine learning model now. So definitely try this one, run this entire code, try different training and test folds, try different random state and see how different performances how are getting different performance. I'll provide you another data set, 1 or 2 data set, just to test your testing on a different data set. So first you have to perform the EDA, see which of features you have to remove or some of the pre-processing is necessary. Then you can actually go for like training your model and see how different performance you are getting. Okay, use cross validation to actually get the ultimate performance and then report it. Okay, any question?
স্যার র্যান্ডম স্টেট যদি ফিক্স থাকতো তাহলে তো ক্রস ভ্যালিডেশন করার দরকার ছিল না, রাইট?
না, ক্রস ভ্যালিডেশন করার দরকার আছে। দেখো তুমি যখন আমরা র্যান্ডম স্টেটটা যদি ফিক্সও থাকি, আমার ডাটা সেটটা আমি যখন ডাটা সেটটা ফিট করতেছি, আমি কিন্তু এই 80% ফিট করতেছি, অ্যান্ড রেস্ট অফ দ্য 20%-এ আমি হচ্ছে আমার টেস্ট পারফরমেন্সটা নিচ্ছি। আমি এইটুকুর উপর ফিট করতেছি, এইটাতে পারফরমেন্সটা নিচ্ছি। বাট হোয়াট ইফ আই চেঞ্জ ইট, if I take the performance on this portion, the performance can be very different because you don't know how the data is actually how the data is divided inside. So these samples can be much more difficult to run compared to these samples. How can I actually judge those things? So it is better to test your model on the entire data set. You see, when I'm using cross validation, after each fold, I'm testing our model on each of the data set. So that means I'm testing on the entire data set and predicting. That's the result I'm getting when I'm using cross validation. If I use only 20%, then I will not get the information, entire information. বোঝা যাচ্ছে আমার কথা?
Yes, sir.
So that's why it's important to perform cross validation. But if you have like a large data set, like 500,000 samples, then it can be very time consuming. Support vector machine classifier will take hours to actually train on that model. So at that scenario, you can actually ignore that cross validation part. And especially in deep learning, we actually don't use this cross validation. In deep learning, we just use train trace split because deep learning is much more computational heavy. Okay. Any other question? Okay, so we can actually finish it for today. Please write your student IDs in the comment section.